Today's goal is to sketch quadratic functions, and by sketch, I'm looking for an approximate graph. I'm saying approximate because you don't have to plot a million points. I just want to see the most interesting characteristics and then the shape that they make together. And we know that quadratic functions make this shape. It's called a parabola. So today, the most interesting points you're going to plot are the intercepts, the x and y intercepts. They should be connected to form a parabolic shape. Let's take a look at our first example. We'll want to start by finding x-intercepts. These are places where the y value is 0. This function factors nicely. So we have two x-intercepts we'll see on our graph. We also want to find any y-intercepts. Those are places where x is 0. So we can take these points and plot them. Again, I'm just giving sort of an approximate location. You don't have to draw all the tick marks up to 4. You can just put 4 if you want. It doesn't even have to be to scale, really. I just want to see these characteristics. The vertex will be halfway between the axes since the function is symmetric. Oops. And I'm just going to connect my intercepts, my approximation of my vertex. So here is my sketch, my approximate graph. Okay, let's take a look at our next example. Again, we're looking for intercepts. Let's start with the roots. Conveniently for us, this function is already factored. So we can just set the factors equal to 0. Here are my two x-intercepts. Remember, I'll always have two x-intercepts. They may be real, they may be complex, or you may have one that counts as 2. But you'll always have two x-intercepts. Let's find the y-intercept by substituting 0 for x. 2 times 0, that'd be 0 plus 1. So g of 0 is -3. Okay, let's plot these points. Again, the vertex will be halfway in between, so maybe about there. Let's connect them. And here is my sketch, my approximate graph. Okay, let's take a look at our final function of the day. Let's find the x-intercepts, or the roots. We've seen one like this before. If we want to expand, let's follow the order of operations by dealing with the exponent first and then multiplying or distributing that -3. I don't know how to factor when this leading coefficient, the number in front of x squared, isn't 1. So let's use our friend the quadratic formula. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. We'll have minus 4 times -3 times -11. So this negative times this negative will make a positive, so we're subtracting 156. I can actually pause here. I notice I'm going to get a negative number underneath the square root. So these are imaginary roots, or two complex roots. That means the function's not actually going to touch the x-axis. So now let's look for the y-intercept. by setting x equal to 0. H of 0 is 3 times the quantity 0 plus 2 squared plus 1. We follow PEMDAS, we do what's in the parentheses, then we square, then we multiply, and then we add. So we have a function that has a y-intercept at 0, 13. But my question to you is, will it look like this with a vertex in quadrant 2? Or will it look like this with a vertex in quadrant 1? Or would it actually look like this where the y-intercept is the vertex? It's a little hard to tell without having any x-intercepts to connect the dots, which is why it's important that we have the vertex form of a quadratic function. And vertex form is this: f of x equals a times the quantity x minus h squared plus k. We'll have a vertex at the point hk. Notice it's the opposite x value and the same y value that you see in the function. Let's take a look back at our original function for example 3. This function will have a vertex at -2. I'm taking the opposite x value, +1, same y value, same sign, +1. So the vertex is at -2, 1, which means it'll look like this blue function here. And in fact, if we were to redo this problem knowing vertex form, let's actually do that. We would have a much faster time of it. H of x is 3 times the quantity x plus 2 squared plus 1. We would know right away it has a vertex at opposite x sign, so -2, same sign, +1. Finding the y-intercept was easy. We substituted x as 0. That didn't take much work. We got the y-intercept at 0, 13. So we could have plotted these 2 points, -2, 1, 0, 13, and saved ourselves a lot of time by thinking if we connect them right away, we definitely won't have any x-intercepts. We could have concluded just by the sketch itself that there would be no real roots, or said in a different way, 2 complex roots. You would not have had to go through all of this work now that you recognize what vertex form is. Now, you can stop here if you'd like, but I want to challenge you to look at this proof. It isn't easy to find the vertices in examples 1 and 2 unless you know something special. So example 1, the function is given in what's called standard form because it looks like ax squared plus bx plus c. This is standard form. And example 2 is given in factored form because it looks like x minus r1 times x minus r2, I'm using r for roots, is equal to y. Example 3 was given in vertex form, right? Vertex form, it's clear where the vertex is. In other forms, it's not clear where the vertex is unless you consider this proof. Now, parabolas are always symmetric, meaning they're not going to be really wide on the left and really narrow on the right. They're always going to be symmetric. So since parabolas are always going to be symmetric, wherever your roots are, the vertex will always be halfway in the middle. So if you have a root at -b plus the square root of b squared minus 4ac all over 2a, and you have another root at x equals -b minus the square root all over 2a, that's where your roots always are. Remember, the quadratic formula always works. Then the x value of the vertex is the midpoint or average of the x values of the roots. To find an average, we're going to add up 2 roots and then divide by 2. So we're going to add up these roots, x plus square root of b squared minus 4ac all over 2a, and x minus the square root of b squared minus 4ac all over 2a. When we add them up, you're adding a root, you're subtracting a root, so those will cancel out. So the x value of the vertex is at x plus x, that's 2x all over 2a, divided by 2. These 2's cancel. The x value of the vertex is at x over a. Dividing by 2 is the same thing as multiplying by 1/2. So the x value of the vertex is at x over 2a. Oops, I'm so sorry. This should be negative b in our quadratic formula, which makes this negative b over